Hi, and welcome to The Dreaming Scientist, a quiet place in deep space with softly spoken science for sleepy minds. Tonight we are going to talk about a calm but huge question. Could Mars have hosted life? Not red dust and cold winds like today, but an earlier Mars, when it was warmer, wetter, and fresh from its birth. We will move slowly through how Mars formed, how it held water, how it lost its shield, what the rovers found, and why small, tough life could have lived there underground or in lakes. But before we get into today's video, take a moment to like the video and subscribe to the channel. Also comment down below where you are watching from. It is always intriguing to know who is watching us from around the world. I also want to say that I appreciate you all for being here. When the solar system was young, Mars was not born as a frozen desert. It came out of the same dusty, icy, rocky mix that built Earth. Both Earth and Mars formed in the inner part of the solar system, where sunlight isn't too weak, so both of them got a shot at being wet. Early Mars almost certainly had hot insides from impacts, from radioactive elements, from the simple heat of being squeezed together. A young hot inside means volcanoes, gases coming out, and a thicker early atmosphere made from that gas. If you have a thicker atmosphere, you can hold warmth. If you can hold warmth, liquid water can lie on the surface and flow. That's the Mars we care about, the Mars before it thinned out. But there was a built-in problem. Mars is small. It's only about half Earth's diameter and about a tenth of Earth's mass. In planets, size is staying power. Big planets cool slowly, keep their cores moving, keep their magnetic shields on, and hang on to air. Small planets cool quickly, their cores slow, their magnetic fields fade, and the sun's wind can start peeling their air away. So while Earth was big enough to stay alive inside for billions of years, Mars was always on a clock. It got to be nice, but not forever. That's exactly why Mars is such a good question. Life on Earth seems to have shown up fast, within a few 100 million years once things settled. Mars probably had a few 100 million years of being much friendlier than now. So right away the thinking becomes, if life can start quickly and Mars had water, warmth, and the same basic raw materials, was that time window long enough? We don't have to imagine jungles or animals on Mars. We only have to imagine tiny cells, films, mats, things like the earliest Earth microbes that lived in lakes or shallow groundwater. Mars had the chemistry. Mars had the water. Mars had the timing. What it didn't have was Earth's long endurance. That difference, enough time versus not enough time, is the main thread in the whole Mars life story. If Mars had really been dry forever, the surface wouldn't look the way it does. When orbiters started taking sharp pictures, scientists saw valley networks, long branching channels that look almost exactly like dried-up river systems on Earth. They start small, they join together, they flow downhill, and they sometimes empty into basins. Wind doesn't make that kind of tidy dendritic pattern. Liquid water does. Even better, Mars has huge outflow channels, big, smashed-out paths that look like sudden floods blasted through. So we have signs of both steady runoff and occasional big releases. You don't get that unless you had liquid water at the surface. Some of these valleys are very old, more than 3.6 or 3.7 billion years old, which is the same overall era when Earth was first getting life going. So right when Earth had little microbes learning to live in water, Mars had water too. That's a powerful overlap. Later, when rovers drove across the ground, they didn't just see channels from above, they saw the leftovers rivers make. Curiosity saw rounded pebbles. A stream rolls rocks together and bumps them so their sharp edges break off. You need flowing water over some time to do that. Spirit and Opportunity saw cross-bedded layers, slanted layers built by moving water. Taken together, orbit images say this was a river. Ground photos say this was a river, and the minerals say water stayed here. Rivers also tell us about climate. To have rivers, you need not just water, but water cycling, snow or rain or melt coming back again and again. That hints at an atmosphere that could keep heat for a while, not the thin air Mars has now. So every winding valley on Mars is like a finger pointing back to a time when being a microbe on the surface wasn't crazy. Water moved, sediment moved, chemistry had time to happen. That is exactly the kind of setting early life loves. One of the nicest pieces of evidence for ancient habitability on Mars is the crater lake. A crater is just a big hole from an impact, but if later on we see a river going in and a river going out and flat layered stuff in the middle, that crater held a lake. Jezero, where Perseverance is that exact story. A river entered, spread out, dropped a delta, and water sat there. A lake is better than a flash flood for life. A lake keeps water around. A lake lets fine mud settle to the bottom. A lake can stay stable for thousands of years, maybe longer if the climate allows. That's enough time for microbes to colonize the muddy bottom, make slimy mats, and get buried. Delta deposits are extra exciting. A delta is like a conveyor belt for tiny things. Fine clay, organic bits, maybe even cells, all get carried in, then slowed down and dropped right at the front of the delta. Then the next flood drops more on top. That fast burial is what we like on Earth when we go looking for ancient life. It protects delicate stuff from light and radiation and being scraped away. Mars has at least a few places like that, and we are now driving through one. That's not hand-waving. We picked Jezero exactly because the volume and shape of the delta says water kept coming for a while. A lake also proves something about the air. On today's Mars, water can't just sit in a pond. It would freeze or boil off because the pressure is too low. So if there was a lake, the air was thicker and probably warmer back then. Thicker, warmer air plus standing water plus fresh sediment is basically the starter kit for early microbial life. We don't know yet if Mars used that kit, but the kit was there. That's the key idea. Water doesn't just carve, it reacts. On Mars, orbiters and rovers have both found minerals that must have formed in the presence of liquid water. The big one is clay. Phyllosilicates. Clay forms when water sits with volcanic rock and slowly changes it, stripping some elements out and making soft, layered minerals. That takes time and water, not just a single splash. Clays are great for life because they can trap organic molecules between layers. Mars also has sulfates, minerals that can form when water evaporates and leaves salts behind. That tells us there were basins that filled and dried. We even see some carbonates, which need carbon dioxide-rich water and rock in contact. So we don't just have maybe water ran here once, we have a timeline of water, very wet, clays, then more episodic and salty, sulfates, then mostly cold and dry. The really old terrains on Mars, Noachian terrains, are the ones richest in clays. That lines up with the river story. Early Mars was the wet Mars. Later Mars was the drying Mars. That's exactly the order we'd want if we're hoping for life to appear, then slowly retreat underground. On Earth, a lot of our oldest hints of life are in fine-grained sedimentary rocks changed by water. Mars has the same style of rocks in the right age window. That doesn't prove anything by itself, but it means Mars built the same kind of shelves where life's handwriting normally shows up. And one more thing. These minerals tell us about pH and saltiness. Some Mars waters were not extreme. Curiosity measured lake muds that were basically drinkable, not super acidic, not super salty, and had elements like nitrogen and sulfur life could use. That's huge. We don't have to make up some weird alien chemistry. We can say, this water here would have worked for microbes we already know on Earth. So Mars wasn't just wet. Parts of it were friendly wet. So if Mars was doing so well, how did it end up thin, cold, and dusty? The most convincing story is that Mars lost its magnetic field early. Planets get a global magnetic field when they have a hot, moving, electrically conducting core, like liquid iron, and that motion acts like a dynamo. Earth still has that. Mars, being smaller, cooled faster. Its core motion slowed. When the dynamo weakened or stopped, Mars no longer had a big magnetic bubble to push the solar wind away. The sun constantly blows out charged particles. If they can reach the top of an atmosphere, over millions and billions of years, they can knock gas into space. NASA's MAVEN spacecraft actually measured Mars losing air right now. It's not fast today, but over deep time it adds up. Once the air thinned, a few bad things happened for surface life. First, pressure dropped, so liquid water couldn't stay on the surface for long. Second, greenhouse warming dropped, so the planet got colder. Third, more radiation hit the surface, which breaks apart complex molecules. Put together, that means surface habitats got worse and worse. A planet that could once support lakes became a planet where lakes could only form briefly, maybe after an impact or volcanic event. This is why everybody keeps pointing to early Mars as the best window. That's when the shield was still working or had only just faded. That's when the atmosphere was at its thickest. That's when rivers ran most widely. That's when the most promising minerals formed. If life ever got started, it probably started then. After the shield died, Mars didn't instantly die, but the easy places to live slowly disappeared. Anything that wanted to keep going had to do what microbes on Earth do in deserts and permafrost: go down. Surface Mars today is rough, cold, dry, hit by radiation. But just a few meters down, things calm down a lot. Radiation falls off quickly with depth. Temperatures are more stable. If there's buried ice, and Mars has lots of buried ice, you can melt tiny amounts in the right conditions, especially if salts are present. Salty water, brine, stays liquid at lower temperatures than fresh water. That means cracks, pores, and little sediment pockets underground could have held films of liquid long after the surface froze. On Earth, we have a huge deep biosphere. Microbes living in rock, eating the rock, using chemical reactions as their power source. They don't care about sunlight. They don't even care about seasons. They just need water to move chemicals around and minerals that can be oxidized or reduced. Mars has basaltic rocks, iron-bearing minerals, sulfur minerals, all the stuff deep microbes like. If water ever percolated through those rocks, even slowly, it could have set up those tiny chemical gradients microbes love. So even as the surface of Mars got worse, the subsurface could have stayed good enough. Underground is also where organics survive. Cosmic rays and UV can shred organics on the open ground, but bury them under sediments in a delta or under volcanic ash or just a couple meters of dust, and they can last for hundreds of millions or even billions of years. That's why so many Mars missions talk about drills and sample return. We want the stuff that hasn't been cooked by 3 billion years of radiation. If Mars ever had life, the most honest pieces of it are probably still down there, waiting in the dark. If you want life on a planet that's slowly getting worse at the surface, one of the best gifts you can get is internal heat. Mars had that. We know Mars had powerful volcanoes because Olympus Mons is there, 24 kilometers high, bigger than anything on Earth. You don't get a volcano that big unless the inside was moving hot rock upward for a long time. And where you have big volcanoes, you don't just have lava. You have hydrothermal systems, places where hot rock warms water and drives it through cracks. On Earth, those places are gold for microbes. Even miles under the seafloor, at black smokers, life gathers around hot, chemical-rich water. It doesn't care that there's no sunlight. It cares that hot water is meeting cold water and releasing energy. Now move that idea to early Mars. Picture a thick stack of lava plains, the Tharsis region, slowly cooling. Ice or groundwater sits nearby. The hot rock warms the water. The water starts to circulate. It picks up minerals. It rises in vents, seeps through warm sediments, maybe makes little silica mounds like we see at hot springs on Earth. That water is full of chemical gradients, reduced iron meeting oxidized iron, sulfur in different states, maybe even hydrogen from rock-water reactions. All of those are things microbes can eat. So even if the global climate on Mars was drifting toward colder and drier, these volcanic provinces would have stayed locally friendly for a long time. We've even seen hints of this in the data. The Spirit rover found light-colored, almost pure silica patches in Gusev crater. On Earth, that kind of silica can form at fumaroles or hot springs, where acidic hot water leaches everything else away. Curiosity has seen altered rocks that match low-temperature water-rock reactions. From orbit, we see minerals like opaline silica and certain sulfates in or near volcanic terrains. None of that is, here is a microbe, but it is. Here is the kind of plumbing that microbes love. And remember, hydrothermal spots don't need the atmosphere to be perfect. They make their own small warm zone. So as Mars was losing air and cooling at the top, down in these hot rock neighborhoods, the clock was ticking slower. Life would have had a chance to retreat to those places and keep going, or even start there in the first place. Add to this the fact that big impacts act like temporary volcanoes. A big rock slams into Mars, melts ice, melts rock, and leaves a crater with a hot interior for thousands of years. Water circulates, minerals form, gases escape. On a planet with lots of impacts early on, that means lots of brief hydrothermal oases. If life can take hold in decades on Earth around hot springs, it could do the same on Mars around an impact-heated crater. So Mars was not just wet once. It was wet in bursts again and again, with heat right where water was, and that pattern is exactly what keeps habitability alive even as global conditions head downhill. Rovers are slow, but they make the argument hard to break. Spirit and Opportunity showed first that some Martian rocks were soaked, then dried, then soaked again. Opportunity, at Meridiani Planum, rolled over layered sandstones filled with little blueberries, hematite concretions, that form when water moves through sediments and precipitates iron. It also found sulfate-rich rocks that looked like they were laid down in shallow, sometimes salty water. That alone told us water didn't just flow, it stayed and evaporated. Then Curiosity went to Gale Crater and made the case even harder to ignore. It drilled into fine mudstones right in the middle of the crater and found they were once the floor of a calm lake. Grain sizes showed still water. Layering showed long-term deposition. The chemistry showed the water wasn't crazy acidic or crazy salty. It was, in NASA's own words, habitable. Not life was here, but life could have lived here. Big difference, but still a strong one. Curiosity also sniffed organic molecules in those mudstones. That is huge, but it needs to be said slowly. Organics are carbon-bearing molecules, and they can be made by non-living processes. Meteorites bring organics. Volcanic processes can make organics. So finding organics is not proof of Martians, but finding them in ancient lake muds in a place with nitrogen, sulfur, phosphorus, and a nice pH is like finding flour, eggs, sugar, and a working oven in someone's kitchen. You still don't know if they baked, but every piece to bake was there. Then we sent Perseverance to Jezero Crater, a place that from orbit clearly shows a delta. It is now coring the very kind of rocks on Mars that on Earth would be our best bet to find old microfossils. And instead of trying to do everything there, Perseverance is caching those cores for Mars sample return. So the surface truth as of now is, Mars once had lakes. The lakes lasted long enough to lay down layered mudstones. Those mudstones preserved organics. The waters were chemically friendly, and different parts of the planet saw water at different times. That's a lot of green lights for habitability. If your rule is don't make life up, that's fine. We're not. We're just stacking observations until the way to bet becomes obvious. Early Mars was a place where microbial life could have started and could have been preserved. The rovers basically turned maybe it rained into no, seriously, this was a lake. Looking at today's Mars, it's fair to say, well, where is it then? We see dry riverbeds, not rivers. We see dusty deltas, not lakes. We see a thin CO2 atmosphere you could almost ignore. But Mars still has a lot of water, just not where you expect it. The poles hold thick stacks of water ice layered with frozen CO2. Radar instruments on orbiters have seen buried glaciers at mid-latitudes covered by dust. Some craters show bright ice in freshly cut scarps. So the planet didn't lose every drop. A lot of it got locked up as ice once the air got too thin and cold to let it flow. Another chunk did escape to space. MAVEN measured oxygen and other ions being pulled off Mars' upper atmosphere by the solar wind right now. We can back that loss up over billions of years and see that a thick early atmosphere could indeed be shaved down to today's wispy one. Some water also got mineralized, turned into water-bearing minerals like clays. That traps water in the rock itself, and some may be in deeper aquifers we can't easily see yet. So the picture is, early Mars had surface water because it had more air and more warmth. Then the magnetic field died, the solar wind had a clearer shot, the air thinned, the greenhouse dropped, and surface water was forced either to freeze, to go underground, or to be lost upward. That doesn't make early lakes imaginary, it just means they couldn't last forever. For life, that's not the end. Lots of microbes don't need endless oceans. They need a few million years of good conditions and then a way to hide. Mars offered both. First the good, then the hiding spots. That's why modern Mars looks dead, but can still hold the record of not dead in its rocks. One of the coolest, messiest things on Mars right now is methane. Curiosity, sitting in Gale Crater, has sniffed the air many times and found that the methane level is usually very low. Then sometimes there's a spike. Some orbiters have seen methane too, though not always in the same place or at the same time, which is why scientists still argue about it. The key fact is this: methane in Mars's thin, UV-bathed atmosphere shouldn't last very long. Sunlight and chemistry break it down, so if we see methane, something must be adding it. There are two sensible sources. One is abiotic, non-living. If water reacts with certain rocks, like olivine-rich volcanic rocks, it can make hydrogen, and that hydrogen can go on to make methane. This process, called serpentinization on Earth, happens in some ocean crust and makes methane without any microbes helping. Mars has the right kinds of rocks, and it once had water, so this is a real path. The other path is biotic, from life. On Earth, small microbes called methanogens make methane as a waste product when they eat simple chemicals in oxygen-poor environments. If anything like that survived in Mars's subsurface, it could be making tiny amounts of methane that leak out through cracks. Right now, we can't tell which it is. The amounts are small, the pattern is patchy, and Mars is hard to measure from far away. But just the fact that methane comes and goes tells us Mars is not perfectly still. Gas is moving. Rock and water might still be reacting. Maybe even cells are. On a planet that looks frozen, it's important to find any sign of present activity, because active places are where habitability still exists, even if only in tiny local underground pockets. Later missions that can sniff methane closer to the ground and trace it upwind to a source will be able to tell us whether we should send a drill there right away. When a planet cools and loses air, normal liquid water should stop working at the surface. It should either freeze into solid ice or disappear into vapor. But Mars has a trick, and the trick is salt. Salts change the rules for water. On Earth, if you pour salt on an icy road, the ice melts even though the air is below freezing. That's because salt lowers the freezing point. Mars has salts too, and not just table salt. It has perchlorates, sulfates, and other salts we've actually detected with landers and rovers. Perchlorates, in particular, are very good at letting water stay liquid at temperatures where you and I would expect it to be solid. So even on modern Mars, with its thin, cold air, there can be thin films of salty water that form for short times. Now, these are not pretty blue lakes. These are not even puddles. Think instead of damp soil, or a hair-thin wet layer between grains of dust, or a salty trickle on a warm slope in late spring. To us, that sounds miserable. To microbes, especially ones like we find in Earth's cold deserts or salt flats, that can still be enough. On Earth, we find life in the Atacama Desert living in salty crusts, where just a little humidity lets water cling to salt. We find life in Antarctic sea ice, where briny water runs in tiny veins even though everything looks frozen. Mars could do the same thing, cold on the outside, but salt keeping water liquid in tiny hidden spaces. Salts also do something else that matters for the story. When water evaporates, it leaves salts behind, and those salts can trap whatever the water was carrying. Organics, fine clay, even possible cell pieces. That means salty deposits from ancient Mars could be small time capsules from a phase when water was still moving. If you core through them, you might find what the water was doing that day. So even though salty Mars sounds like dry Mars, it actually means Mars pushed water to the edge and kept it going in the only way it could. For life, that's not bad news. That's Mars doing everything it can to stay habitable a little longer. To tell if Mars could host life, we have to be fair about what life looked like at that time in the universe. It didn't look like trees and fish. On Earth, the earliest life we know about is small, simple, and tied to water. We have rocks more than 3.5 billion years old that show layered structures called stromatolites, made when sticky microbial mats trap sediment over and over. We have chemical signatures in very old rocks where carbon is skewed toward the lighter isotope, which is something life often does. We even have tiny cell-like shapes trapped in minerals. None of these are dramatic. You would walk past them on a beach, but together they tell us, as soon as Earth had stable water, life moved in. Now match that to Mars. Mars had stable water, rivers, lakes, deltas, at roughly the same ancient time. Mars had volcanic heat. Mars had the basic elements life uses: carbon from CO2, hydrogen from water, nitrogen in small amounts, sulfur and phosphorus in minerals. So if life can start easily when rock, water, and energy meet, Mars should have been in the running. The difference is that Earth kept feeding that life with a thick atmosphere, plate tectonics to recycle nutrients, and a magnetic field to guard the air. Mars, being small, couldn't keep giving. So Mars is like a classroom where all the students showed up, the teacher started the lesson, and then the lights went out. Did the lesson get far enough? That's what we're asking. This comparison also keeps us from demanding too much. If Mars did make life, it would probably look like Earth's early life. Thin mats, slime on the bottom of a lake, tiny cells in mud, not giant fossils waving at a camera. So when we point cameras and drills at Mars and don't see big life, that's not a fail. That's us looking for the wrong thing. We should be looking for layered mud in deltas, for tiny carbon signals, for minerals that formed slowly in calm water. And good news, Mars has all of those. It built the same kinds of rocks that, on Earth, are full of life's earliest handwriting. When we talk about could Mars have hosted life, we are really asking, did Mars stay nice long enough for simple life to start and settle in? Water for one day is cute but useless. Water for millions of years is when chemistry can keep repeating until it finds a winning pattern. Mars actually lets us see that its good period wasn't just a flash. The oldest surfaces on Mars, the Noachian, more than 3.7 billion years ago, are full of things that only running or standing water make. Long valley networks, lake basins, thick clay-rich crust. That means during that era, water wasn't rare. It was part of the landscape. Entire regions were being shaped by it. You don't carve hundreds of kilometers of valleys in a weekend. You do that in climate conditions that keep coming back. Snowmelt every year, rain or at least precipitation, groundwater moving. Then Mars seems to shift into the Hesperian. Here the story changes a bit. We see more volcanic plains, more sulfates that form when water evaporates, more signs of episodic water. Big floods, not constant flows. That says the planet was cooling and the atmosphere was thinning. But cooling isn't dead. Even in this drier era, there were deep basins that could hold water, places where groundwater could seep out, and melt events tied to impacts or volcanoes. After that, in the Amazonian, the most recent and longest period, Mars is mostly cold and dry, with water locked as ice, and liquid water only appearing in very local, short-lived ways. That sounds bad until you put all three eras together. You get a very wet start, a long middle of patchy wet, and a long cold tail with pockets. Add that up, and you have many hundreds of millions of years, maybe more than 1 billion in total, during which somewhere on Mars was friendly. Why is that enough? On Earth, once the surface calmed down from non-stop impacts, life shows up fast. In the first few 100 million years, we can see signs. Mars had a wet, chemically active surface in that same broad cosmic moment. So even if Mars was losing atmosphere in the background, the moment when water, rock, and energy were all available overlaps with the moment when life tends to appear. After that, as global surface conditions worsened, habitability didn't vanish. It retreated. Deep sediment basins, volcano-heated spots, and aquifers could have stayed good for far longer than the average climate. That's exactly the kind of staggered, shrinking habitability zone that simple, tough microbes could follow. So the honest read is, Mars' nice window was not permanent, but it was long enough to be biologically meaningful. Water lets life move stuff around, but life still needs a power source. On modern Earth, we think sun first, but on early Earth, and on a cooling world like Mars, chemical energy becomes the star. Mars's crust is basaltic, full of iron, magnesium, and other elements that react with water. When water moves through fresh volcanic rock, it can make hydrogen gas. Hydrogen is like candy for many microbes. They pair it with carbon dioxide and make methane or other simple organics. Mars also has sulfur-bearing minerals. On Earth, there are microbes that breathe sulfate or reduce sulfur instead of using oxygen. Mars had sulfate-rich waters in some places. Opportunity rolled right over those. That's another redox couple life could have used. Then there's iron. Mars is red because iron got oxidized. It reacted with oxygen. But not all iron would be in the same state everywhere. In a lake, or near a hydrothermal vent, or underground in low oxygen water, you can get both oxidized and reduced iron close together. Microbes love that. They take electrons from one form and pass them to the other, and in doing that, they get energy to build cells. None of these pathways require thick air, green plants, or bright sunlight. They just need liquid water to act as the delivery truck for ions, and rocks that still have some chemical tension in them. That's important for a Mars that's losing atmosphere. As the sky thins, photosynthesis on the surface becomes harder. Too much UV, not enough stable liquid water. But chemistry underground doesn't care about sunburn. If there was once a water table, or if there are still briny pockets moving through volcanic rocks, those places could stay energetically habitable long after the surface froze. This is why a lot of Mars life models talk about chemolithotrophs, rock eaters, hiding in the subsurface. They match the planet's trend. Surface got worse, but the rocks still had food in them. So when we say Mars could have hosted life, we don't mean palm trees. We mean very patient microbes quietly running redox reactions in dark, wet cracks. One of the biggest differences between Earth and Mars today is how much protection the ground gets from space. Earth has a thick atmosphere and a strong magnetic field, so most of the worst space stuff never reaches the ground. Mars used to have more of a shield, but it lost it early. Once the magnetic field faded and the air thinned, the surface became exposed to two things that slowly erase delicate chemicals: ultraviolet light from the sun and high-energy particles from space. Those two together act like a constant slow sandblaster on organic molecules. If you leave complex carbon compounds sitting right on top of Martian soil for millions or billions of years, they will be broken down into simpler, less useful pieces. That's why when some landers looked for organics in the uppermost soil decades ago, they didn't see much. They were looking in the part Mars has been cleaning for ages. But this harshness is a very shallow problem. Radiation loses strength quickly as it goes through material. Even a few centimeters of dust or rock cuts it down a lot. A meter or two below the surface, conditions are already much better for long-term survival of organics and for microbes too. So Mars is basically setting a very reasonable rule for survival. You can live here, but not right on top. Any microbe that could move down into pores, cracks, buried lake muds, salt layers, or ice would suddenly find itself in a calmer world. Less radiation, more stable temperature, more chance that tiny films of water stay liquid. On Earth, we actually see this behavior in our own deserts and cold valleys. The life is often not on top, but under rocks, inside translucent stones, or a little way down where moisture stays. Mars is just that strategy turned up. This is also why our search strategy has to drill, core, and look at buried sediments, not just surface dust. The places that can still hold a record of ancient life are the ones that were covered quickly, like delta mud at the bottom of a crater lake, or the ones that have never been at the surface since the wet era. A thin cover of sand, or a layer of volcanic ash, or impact debris could have protected a fossilized biofilm for billions of years. So radiation is not the end of the Mars life story. It's the clue that tells us where the remaining pages are. Life on Mars, if it kept going after the atmosphere thinned, would have followed the water downward and let the dirt take the hits for it. Right now, we're very good at saying, this was a lake, this was laid down in calm water, and this rock still has organics in it. Our rovers did that. Curiosity drilled Gale Crater mudstones and found ancient, not too salty, not too acidic lake deposits with organic molecules and elements like nitrogen and sulfur. Perseverance is doing the same at Jezero, but in a place with an obvious delta, the exact place we'd expect river-delivered organics to pile up. That already proves habitability, but habitability is not the same as inhabited. To tell those two apart, we need measurements that are too delicate, too high resolution, or too complicated to fly to Mars right now. That's the whole point of Mars sample return. Pick up the best rocks, bring them here, and let Earth's full lab power take over. What would we do with them? We'd slice them thinner than a hair and look for tiny structures that repeat in ways minerals don't. We'd measure carbon, sulfur, and nitrogen isotopes to see if the light versions are just a little too common, a classic sign that biology was choosing them. We'd separate all the organic compounds and see if they look like random meteorite organics or like molecules that have been through cells. We'd date the minerals in the sample precisely to make sure they formed in the era when Mars was wet. And we'd compare several samples from different spots in the same ancient lake to see if the pattern holds. That's how you build a courtroom-level case. And there's a nice honesty to it. If we do all of that on the best lake muds Mars has, and we don't see biological patterns, then we can say with confidence, Mars had water, chemistry, and time, but we don't see life. That's still a good result, because it tells us water and rock alone aren't always enough. If we do see biological patterns, then it's even better. We can say, life started right next door when it got the chance. Either way, the way to stop guessing is to bring the rocks home. Everything we've seen so far has been Mars telling us, I set the table. Sample return is us finally checking the plates. There's a quiet part of the Mars story that makes could Mars have hosted life a lot more believable, and it doesn't happen on Mars at all. It happens in space between Mars and Earth. We already know for a fact that chunks of Mars have landed on Earth. We can hold them. They're Martian meteorites. Scientists looked at the gas trapped inside the tiny bubbles in those rocks and saw that the gas matches the Martian atmosphere measured by Viking. That means a big impact hit Mars hard enough to throw pieces of Mars into space. Some of those pieces drifted for a while, and eventually one of them fell through Earth's sky. If Mars to Earth transfer is possible, then in the early solar system, when impacts were bigger and more common, Earth to Mars transfer is also possible. Rocks were flying both ways. Now imagine early Earth. It seems to have gotten life going fairly quickly once its surface cooled, within a few 100 million years. At the same time, Mars was also young, still warm inside, still holding a thicker atmosphere, still running water on its surface. If an impact on Earth blasted out rocks that had hardy microbes sealed inside tiny pores, some of those rocks could have landed on Mars while Mars was still friendly. The rock would shield the microbes from radiation, from cold, and even from the heat of entry if the angle was right. We know there are Earth microbes today that can survive vacuum, drying, freezing, and high radiation. Ancient, tough microbes could have done it too. In that case, Mars didn't have to invent life from scratch. It just had to host life that arrived during its wet window. Flip the direction and it still helps. Mars may have cooled faster in some places, so parts of Mars may have been habitable slightly earlier than Earth's surface. If Mars got a head start, it could have made its own simple microbes and then, during an impact, launched them toward Earth. That would make Earth and Mars part of the same early biosphere, not two lonely experiments, but two labs trading samples. That's called lithopanspermia, and it sounds sci-fi, but the physics part is already proven by the meteorites. The only missing piece is the biology, and biology on Earth keeps surprising us with what it can live through. Why does this matter for your video? Because it moves the question from, could Mars have done the whole life thing alone, to could Mars have stayed hospitable long enough to receive life or to share it? That's an easier bar to clear. If you're wet, warm, have lakes and volcanoes, and you get delivery of living cells from next door, then yes, you could have hosted life. And it gives you a nice hook for the end. If we one day find life on Mars that looks chemically just like early Earth life, we'll have to ask, did we send it there, or did Mars send it here, or were both planets swapping seeds back when everything was young? So far we've been talking about Mars billions of years ago, when rivers actually ran and lakes actually filled craters. But people always want to know about now. Could Mars have hosted life? Quickly becomes, could Mars still have life? And the gentle, honest answer is, if Mars has any life today, it's not living on the wide, dusty plains in the open. It's doing it quietly in small, protected places that stay just a little bit warmer, wetter, or safer than the rest of the planet. Mars is mostly a freezer, but even freezers have corners that don't get as cold. One of the best candidates is lava tube caves. On Earth and the Moon we see them, long tunnels left behind when the outer skin of a lava flow cooled and the inside kept flowing out. Mars has huge old volcanic regions and lower gravity, so its lava tubes could be large, stable, and very well shielded. Inside a cave, you don't get blasted by UV and cosmic rays. Temperatures don't swing as hard as day to night. If water vapor enters, it can condense and stay on walls. If there is ice in the roof or floor, a little bit of heat from the ground or from seasonal warming can melt a thin film. That environment is instantly friendlier than the open, dusty surface. A microbe that lives off chemical energy, not sunlight, could make that its home. Another little oasis can happen where salts and ice mix. Mars has perchlorate salts that are very good at grabbing water and lowering its freezing point. That means on a sunny day, when the top few centimeters of soil warm up, a salty patch can briefly become damp or even liquid while the air temperature is still below zero. It might only last hours. It might only happen in certain seasons. But for a microbe that spends most of its time dormant, waiting, that is enough time to wake up, repair itself, maybe divide once, and then go back to sleep. On Earth, in the Atacama, we see microbes doing exactly that. In some years, they only get water from fog or from salt taking water from the air, and they still survive. Even fresh impacts can make short-lived oases. When a meteoroid hits ground that has buried ice, the impact energy melts some of that ice. For months or even a few years, the crater floor and walls could be warmer and wetter than normal. That's a blink to a planet, but a long time for microbes. So modern Mars habitability is patchy, time-limited, and deep, not broad, constant, and shallow like early Mars. That's why we don't see obvious life from orbit. It would be in caves, in cracks, under boulders, in salt veins. But the simple fact that Mars can still make any of these microhabitats today makes it far more believable that, in the past when it was broadly wetter, it could host life much more easily. Because we can't yet walk around Mars with a hand lens and a shovel, we practice on Earth in places that are as close as we can get. And Earth actually has several places that act like little Mars test beds. The Atacama Desert in Chile is one. Parts of it are so dry and salty that for a long time people thought nothing at all could live there. Then researchers started looking not at the open soil, but inside salt crusts, and found microbial DNA and even living cells. The salt was pulling tiny amounts of water from the air and holding it. Inside that salt, light was dimmer, UV was blocked, and the microbe had just enough water to run its chemistry. That's exactly the kind of trick life on Mars would need to pull. Then there are the Antarctic dry valleys. Cold, windy, barely any liquid water, lots of UV when the sun is up. Yet microbes live under translucent rocks, where the rock filters the light, blocks the wind, and holds a little moisture. In permafrost, microbes can stay alive for tens of thousands of years, basically in suspended animation, waking up again when the ground thaws a little. All of those strategies have something in common. Life shrinks its scale. It doesn't demand a lake. It demands a microhabitat. It uses the geology, salt, rock, ice, as its shelter. It slows down to match the environment. Apply that to Mars, and the logic becomes clean. We shouldn't expect carpets of lichen or green films across dunes. We should expect little pockets, the underside of a rock that stayed warmer, a salty layer in a crater wall, a cave ceiling with frost, the top of a buried ice lens. That's the level Mars is operating at now, and it's a level life has already proven it can operate at on Earth. That also tells us something important about how to search. We have to go where water was buried fast, deltas, where salts are exposed, where ice is near the surface, and where geology gives natural shielding. Those are the high-value spots, not just any flat plain. There's a second lesson here too. If Earth microbes can live in those harsh Earth spots, some Earth microbes could live on Mars right now if we carried them there by accident. That's why space agencies sterilize spacecraft, and why, when humans go one day, we'll have to be thoughtful about waste and air and drilling. We want to find Martian life, not a Martian colony of Earth extremophiles we dropped off earlier. So Earth's harsh places don't just tell us Mars is possible, they tell us to be careful. Up to this point, everything we've said about Mars has been environmental. There was water, there were lakes, there were rivers, there were minerals that only form in water, and there were volcanoes and impacts that could have made hot springs. That is already a lot. On Earth, those ingredients were enough for life to show up quickly. So it's honest to say, Mars could have hosted life. But saying Mars did host life is a much bigger claim, and science is pretty stubborn about big claims. It wants more than one clue. It wants several different kinds of clues, all in the same rock, all from the right time, and all easiest to explain if life was there. The reason we need several clues is that Mars can imitate life in a few ways. Non-living chemistry can make organic molecules, carbon-based stuff, especially in hydrothermal systems. You can get some organics delivered by meteorites. Evaporating salty water can make strange layered shapes that, in a single snapshot, might look a bit biological. Even isotope ratios, how much of the light version of an element you have versus the heavy version, can sometimes be shifted by non-biological processes, especially if a rock has been heated or shocked. So we can't grab the first weird thing we see and shout life. We have to ask, could this be made without life? If the answer is yes, we keep stacking evidence. So what stack would look strong? First, we'd want organics that look processed, not just random. On Mars, Curiosity has already found organics in ancient lake muds, which is great, but they're fairly simple, and we can't yet tell if they were made by life or by non-living chemistry. In a sample we bring home, we could look for things like complex fatty acids, repeating patterns, or certain ring-shaped compounds that life likes to make in particular ways. Second, we'd want isotopic fractionation, For example, carbon that is a little bit richer in carbon-12 than carbon-13. On Earth, microbes tend to pick the lighter isotope because it takes less energy to use, so the rocks near them end up slightly lighter. If we saw that in very ancient watery Martian rocks, it would make us sit up. Third, we'd want microtextures, tiny shapes inside the rock that look like microbial mats, filaments, domes, or clusters, and that occur in a sedimentary context. On Earth, in calm lakes and shallow seas, microbes make layered carpets that trap sediment, and over time those layers build up. On Mars, in a quiet crater lake, the same thing could have happened. If we slice a Martian mudstone very thin and look at it under an electron microscope here on Earth, and we see tiny repeating cell-sized shapes inside a layer that was clearly formed in water, that's another strong hint. Fourth, we want the right minerals around it. Stuff that forms at low temperatures in liquid water, like clays or very fine laminations, not high-temperature veins or shocked glass. That tells us the environment was calm enough for life to survive and for delicate things to be preserved. Fifth, and this is important, we want to date the rock and make sure it formed in the era when Mars was actually wet, the Noachian or early Hesperian, not a billion years later when the surface was mostly frozen and dry. A beautiful microbial-looking shape in a young wind-blown sand would not help us much. When you put all of those together, processed organics, light-leaning isotopes, microtextures, calm water minerals, and the right age, the explanation this was made by living things starts to become simpler than any non-living explanation. That's where scientists are willing to say inhabited. And that's exactly why Mars sample return is the big move. Our rovers can't do all 5 of those at once with the needed precision. They can tell us this is the right kind of rock, and this has organics, and this formed in a lake. But the fine-grain work needs Earth labs. There's also an important flip side. If we bring back the absolute best, most lake-like, most clay-rich Martian rocks, the very ones a microbe would have loved, and we do all that high-power Earth lab work and still don't see biological patterns, that answer is still powerful. Then we can tell the world, with a straight face, Mars did everything environmentally right, and we still don't see life. That would mean water and rock are not always enough. Maybe you need a thicker, longer-lived atmosphere. Maybe you need plate tectonics to keep recycling nutrients. Maybe you just need more time than a small planet can offer. Either way, Mars helps us draw the line. Habitable is environment. Inhabited is evidence. We have the first, we're going after the second. It's fair for someone listening in bed to wonder, why are we talking about Mars when it's clearly not full of forests or oceans right now? The reason is that Mars is our test world, the one rocky planet besides Earth that we can actually reach, drill, and eventually bring samples back from. Telescopes are finding rocky planets around other stars all the time now, but those are just dots of light. We can measure their size, maybe their temperature, maybe a hint of air, but we can't go there and crawl around in their deltas. Mars we can. And Mars had almost the same starting conditions as Earth, formed in the inner solar system, got warm early, had liquid water on the surface, had volcanic heat, and had the key elements life needs. Then it did something many exoplanets will also do. It cooled, lost its magnetic shield, and started losing its air. That's exactly why Mars is so useful. It's the natural endpoint of small, once wet planet. So here's the big idea. If Mars, with all that going for it early on, shows clear, solid signs that life actually appeared during its wet window, then we have to accept that life is something the universe does fairly easily. It doesn't always need a perfect Earth. It just needs water standing on rock for a few 100 million years, some energy, and the right chemistry. That would mean lots of rocky worlds out there, which were wet for a while and then dried or froze, could have had at least a brief living phase. Tiny, microbial, probably underground, but real. In that version of the universe, life is common, but long-lasting, surface-covering life, like Earth's, might be rarer. If, on the other hand, Mars shows that it did everything environmentally right and still never produced life, we drill its lake beds, we scan its clays, we bring samples home, and we see no biological patterns, then we learn something just as valuable. Life is picky. It doesn't just need water, it needs water for a very long time. It needs an atmosphere that doesn't get stripped too quickly. It might need plate tectonics to cycle carbon and keep climate stable. It might need a big moon to stop wild tilting. It might even need a planet in the right place relative to giant planets, the way Earth is inside Jupiter's general guard. In that version of the universe, Earth and worlds like Earth are the real targets. Mars would become the example of a planet that got close, but not close enough. Either outcome helps us understand the rest of the galaxy. We are not studying Mars for Mars's sake only. We are studying it because it is the only small, once wet, now dry planet we can touch. Venus can't tell us this. It cooked. Europa and Enceladus can tell us about life in oceans, but they're far away and covered in ice. Exoplanets are too far to sample. Mars is the one that says, here's what happens when a planet has a good start and a short run. That's the exact situation we expect for a lot of planets around other stars. And there's another layer, which is good for a sleepy audience. Whatever we find on Mars, we'll learn more about ourselves. If Mars had life, then life in our solar system started at least twice, which suggests the universe is alive all over. If Mars didn't, then life on Earth is even more special than we thought, and it will make people appreciate how much had to go right here. Our size, our magnetic field, our plate tectonics, our distance from the sun. So a video that sounds like it's just about Martian lakes is actually about where else in the universe we might find cousins, or about how rare we might be. That's worth an evening. When we talk about Mars, we spend a lot of time on what it used to be like. Warmer, wetter, lakes in craters, rivers cutting valleys, volcanoes heating groundwater. But there's another part of the story that matters just as much if we actually want to prove Mars could have hosted life. And that part is, we must not mess up the evidence before we've finished reading it. Mars is not just a cold rock. It's a cold rock that, by pure luck, has been storing a 3 to 4 billion-year-old record of water, climate, and maybe even biology. If we barge in without care, we could cover up or even wipe out exactly the signs we've been hunting. Here's the problem in simple terms. Mars today is mostly unfriendly, but it's not so unfriendly that Earth microbes could never survive there. We know Mars has salts that can make very cold brines. We know there is ice just under the surface in many places. We know caves in old lava tubes could shield things from radiation and temperature swings. We know fresh impacts can briefly melt ice and warm the ground. All of those are little windows where life, very slow, very basic, very tough life, could hang on. If those spots exist, they are probably rare and fragile. Now imagine we send something dirty and drop Earth bacteria right on top of one of those rare spots. Suddenly, when a future mission comes and detects life, we won't know if it was Mars's life or our life. That's why space agencies talk about planetary protection. It sounds dramatic, but it really just means good scientific manners. We build rovers and landers in clean rooms. We bake or sterilize parts. We keep track of how many spores might still be on a spacecraft. we plan landing sites away from the most interesting modern water spots unless the spacecraft is clean enough. The goal isn't to make Mars pure. The goal is to make sure that, when we finally find something that looks biological, we can say honestly, that was there before we arrived. The same care goes the other way too. Perseverance is drilling real pieces of an actual ancient delta and sealing them in tubes for a future mission to bring home. Those tubes must stay sealed because we don't want Earth's air and Earth's microbes getting in and confusing the results. And we don't want what's in the tubes getting out uncontrolled, not because we think Mars is hiding monsters, but because we don't yet know the full chemistry or biology of those ancient rocks. Science works best when samples stay what they were. It gets even more serious once humans enter the picture. You can scrub a robot, you can't scrub a person. We breathe out microbes, we shed skin, we have bacteria in our gut, and on our hands, and in our hair. If you land humans right next to a spot where Mars might still have a little bit of liquid water underground, some of our microbes could move in. So scientists are already thinking about rules for human Mars missions. Land away from the most sensitive areas, use closed systems for waste, keep some locations science first, and send clean robots to the places that are the best at preserving old life. It's not to spoil the fun, it's to keep the story readable. All of this care is actually a huge compliment to Mars. We don't do this for every rock in space. We do it for Mars because Mars kept its ancient rivers, kept its lake beds, kept its clays, and might have even kept some modern tiny oases. It has been holding on to those pages for billions of years. We showed up at the very end of the story. It would be silly to smudge the ink now. So could Mars have hosted life comes with a follow-up line, then let's not ruin the proof. One of the biggest reasons Mars is such a good place to look for past life is not just that it was wet, but that it stayed the way it was long enough for us to see it. Earth is amazing for life, but it's terrible for keeping ancient rocks. We have plate tectonics that pulls old seafloor down. We have thick air that erodes mountains. We have oceans that change coastlines over and over. We even have life itself breaking down rocks. A lot of Earth's oldest record is gone, or so changed that it's hard to read. Mars went a different way. It started active, big volcanoes, impacts, running water, and then, because it is small, it cooled down and slowed down. It never grew moving plates like Earth. Its atmosphere thinned, so wind and water couldn't erode as hard. It did not flood and reflood the same places again and again. That means that when Mars made a river valley 3.7 billion years ago, the valley mostly stayed. When a crater filled with a lake and grew a delta, the delta stayed. When water turned volcanic rocks into clays, those clays stayed in the crust, where we can see them from orbit. Mars just left things there. That is incredible for us. It means we can actually go to the real places where water once stood and not just guess where they were. Jezero crater still has its delta shape. Gale crater still has its stack of lake sediments. Huge valley systems in the southern highlands still look like dried-up river networks. We can stand a rover right on top of these things and say, this really happened. We are not working from blurry hints. We are working from preserved landforms. Because Mars didn't erase itself, we can also see transitions. We can see areas full of older, clay-rich rocks that formed in wetter times, and nearby we can see younger, sulfate-rich rocks that formed as things got drier and more salty. We can see volcanic plains that came later and covered up some of the old stuff, but not all. That lets us build a timeline. Wetter early on, slowly drying, then mostly cold and dry. If we ever find proof of life, we can slot it into that timeline and say, life was here during the big wet phase. or life hung on even as Mars was drying, or, less likely, life only appears late, underground. This Mars kept its pages idea is also what lets us choose landing sites so well. From orbit, we can map minerals, clays, sulfates, carbonates, and pick the places that look the most like ancient calm water. We did that for Gale. We did that for Jezero. We can do it again for future missions that will fetch the sample tubes. That is only possible because Mars didn't cover everything with new crust, or grow forests over it, or flood it again and again. It's like the planet thought, I will freeze now. And by freezing, it protected its past. So when we say, could Mars have hosted life, we're not saying it in a vacuum. We're saying it while standing on the very floor of an old lake, looking at the very layers that settled out of that water. That is rare. Most of the time in planetary science, we are forced to guess at the past from scraps. Mars gave us entire chapters. We owe it to that planet to read them properly. Let's weave everything together now, slowly, so someone half asleep can follow it from start to finish without getting lost. Mars formed from the same stuff as Earth. Early on, it was hot inside and had more gas outside, so it could hold on to heat. With enough heat and enough air, water ice can melt and stay liquid on the surface. When that happened, water started shaping the planet. It cut long branching valleys. It filled impact craters to make lakes. Rivers flowed into those lakes and dropped deltas, fans of sediment that buried whatever came in. At the same time, water soaked into volcanic rocks and changed them into clays, which we can still see today. On Earth, those exact conditions, calm lakes, river deltas, water-altered rocks, are where we find signs of early life. While that was happening, Mars's volcanoes and big impacts were heating the crust in places. Hot rock plus nearby water makes hydrothermal systems, and those are some of the best places on Earth for microbes. So early Mars didn't just have one kind of habitable place, it had several. Lakes, rivers, hot springs, impact-heated craters. Add in the fact that Mars had the right elements, carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, and you get a pretty complete starter kit for tiny, simple life. Then Mars's small size caught up with it. Its insides cooled. Its magnetic field weakened or died. Without a strong global shield, the solar wind from the sun could start stripping the top of the atmosphere. Volcanoes were not putting out gas quickly enough to replace what was being lost. The air got thinner. Thinner air means less greenhouse effect, which means the surface got colder. Colder, thinner Mars could no longer keep big, long-lived bodies of liquid water on the surface. Water froze at the poles and in the ground, or it escaped to space. Surface habitability shrunk. But, and this is the important part, it did not go straight to zero. Underground stayed warmer than the surface. Salts could keep little bits of water liquid. Lava tubes could shelter spots from radiation and temperature swings. Impacts and volcanic heat could still make local warm zones. So although the global good times were over, local good times kept flickering on and off. That's exactly the kind of world where life, if it started early, could retreat downward and sideways and keep going in small pockets. Mars then did us a big favor. It froze the record. No plate tectonics tore up the old lake beds. No big oceans reworked all the shorelines. Most of the old valleys, deltas, and water-made minerals stayed where they formed. Billions of years later, we arrived with orbiters and rovers and started seeing exactly what this story predicted. Real deltas, real lake muds, real clays, organics in ancient sediments, water that wasn't too acidic or too salty. The environmental part of the story checks out. Mars really was habitable. Now we're at the last step, proving whether it was actually inhabited. For that, we need the samples Perseverance is caching, and we need Earth labs. But even before we get those samples, the chain already makes sense. Warm start, wet surface, slow drying, habitability moving underground, record preserved. Could Mars have hosted life? Is just the natural question in the middle of that chain. To finish, let's slow the picture down and make it simple again. Imagine Mars as it was, not as it is. The Sun is younger and a little gentler. Mars has more air than it does now, enough to hold some warmth. Dark rock absorbs sunlight. Snow or ice on a crater rim melts and feeds a stream. That stream joins others and makes a small river that winds into a big, round crater. The crater slowly fills and becomes a lake. At the mouth of the river, a delta grows, laying down mud and sand in layers. Exactly the kind of place that buries whatever was living or floating there. Not far away, water deep in the ground is being heated by leftover volcanic warmth and is moving through cracks, carrying minerals and energy. For a while, that is Mars. Not a perfect Earth twin, but a real, working, watery world. Then Mars's small body runs out of staying power. The core slows. The magnetic shield weakens. The sun's wind starts to win and pulls at the top of the atmosphere. The air thins. The blanket comes off. Water can't stay on the surface for long. Lakes dry, rivers stop, the ground freezes. Mars becomes the cold, dusty, quiet planet we see now. But, and this is the reason we can even make a video about it, Mars didn't wipe away the signs of its better days. It left the lake beds, it left the deltas, it left the clays, it left just enough of its old, warmer self that, billions of years later, we could land a small robot and still see what it once was. Maybe, when we finally bring those lakebed samples home and look at them with everything we have, we will find the extra signals, the ones that say, this mud was once full of tiny living things. If we do, that will tell us that life is eager and shows up whenever water and rock cooperate, even on planets that don't stay friendly forever. And if we don't, that will tell us that life needs a longer, steadier run than Mars could give. Either way, Mars will have taught us something huge about how hard or easy it is for the universe to wake up. So we end here, with a small planet that tried to be warm, tried to be wet, and wrote it all down in rock for us. Our job is to read it without smudging it. Thank you for listening. Sleep well, and good night.